Today we're going to look at the 2018 AS Chemistry Paper 1 for AQA. Question 1 is about atomic structure. So we've got a model of J.J. Thomson's plum pudding model there, and we've been asked to state two differences between the plum pudding model and the model of atomic structure we use today. So with the plum pudding model, this takes into no account of the protons or the neutrons, so that can be our first part of the answer. The nucleus we look at now contains protons and neutrons, so nucleus contains protons plus neutrons. Also in the plum pudding model, we know that the electrons are embedded within the molecule, where now we say that the electrons are arranged in shells. So that could be our other part to the answer. The electrons are arranged in shells. Okay. So next part of the question asks us to deduce the full electron configuration of the atom of element R. So if we go back up, we can see that there's 7 electrons. So we need to deduce the configuration for that. So we know we start with 1s, and that has 2 electrons, and we've still got some left over. So we then go to 2s, and that has 2 electrons. So we've accounted for 4 of them, so we've got 3 more to account for. So we go to the 2p, and we put 3 remaining electrons in there. Okay, so the last part of this question says identify R and deduce the formula of the compound when R reacts with the group 2 metal from the same period. So the atom, the element with 7 electrons, we know is nitrogen. And the group 2 element on the same period of nitrogen is going to be beryllium. So when we're deducing the compound that's formed, remember it's got to have no overall charge. Now we know that Be is going to have a 2+ charge, and we know the nitrogen is going to be a 3- charge. So if we have 3 berylliums, we know there's going to be 6 overall positive charges, and that can be taken into account with 2 nitrogens. So that is going to be our formula for Be and N, so there's no overall charge. Looking at the examiner's report, most students did identify N and Be, but many couldn't write the formula. So it's worth practicing this and making sure that you know that when you put the metals and non-metals together, that you've got to put them in such a ratio that there'll be no overall charge. So question 2 involves about concentrations of sodium fluoride in toothpaste, and what we're going to be asked to do is express concentration in different ways. Now some students during the exam got a bit confused between the different methods, so just make sure that you are using the correct method of concentration each time. So we've been told that some toothpastes contain sodium fluoride, and the concentration can be expressed in parts per million, which is 1 milligram for every kilogram of toothpaste. So this part of the question is telling us that 1 gram of this toothpaste contained 2.88 times by 10⁻⁵ moles. says calculate the concentration of sodium fluoride in parts per million for the sample toothpaste and give your answer to 3 significant figures. Now, because it's telling you in the question it's got to be expressed to 3 significant figures, then make sure that you check your answer that you do, or else you're going to lose some marks. So the first thing we need to do is work out the mass of sodium fluoride in this 1 gram, because if we're going to do the concentration in mgs per every kilogram, we're going to have to convert this 2.8 times by 10 to the minus 5 moles into a mass. So the first thing we need to do is work out the molecular mass for sodium fluoride, and that equals 42. So then to convert the number of moles to an actual mass, so the mass of sodium fluoride in 1 gram of the toothpaste is just 2.88 times by 10 to the minus 5 times by its molecular mass, which is 42, and that comes out to be 1.2096 times by 10 to the minus 3 grams. Okay, so the concentration for parts per million, we've got to work out how much are in a kilogram. So therefore the mass that would be in 1 kilogram of the toothpaste would just be times this by 1000, so it'd be 1.2096 grams, which equals, put that into milligrams, because don't forget we've got to, parts per million is milligrams into a kilogram, so that would equal 1209.6 milligrams. So again, all we've done is multiplied it by 1000. So therefore the concentration of sodium fluoride is 1210 parts per million. Okay, now remember it's got to be to 3 significant figures. That's why I've gone from 1209.6 to 1210 parts per million to make sure my answer is 3 significant figures. So part 2 of this question says sodium fluoride is toxic in high concentrations, and the maximum we can have is 3.19 times by 10 to the minus 2 grams for every kilogram of body mass. So deduce the maximum mass of sodium fluoride in mgs that a 75 kilogram person could swallow without reaching toxic concentration. So if it's this mass per every kilogram, all we need to do is do 3.19 times by 10 to the minus 2 times by the 75 kilograms of the mass of the person, and that would be 2.390 grams. Now the question is asking the answer to be in milligrams, so we need to convert this 2.390 grams into milligrams. So again, we just times it by 1000, so that becomes 2390 milligrams. Question 3, it says the concentration of sodium fluoride in a prescription toothpaste is 2800 parts per million. Use our answer to the previous part to deduce the mass of toothpaste in kilograms that a 75 kilogram person could swallow without reaching the toxic concentration. So we know that the maximum that they can have in parts per million in the last question was 2,390. Now obviously this is much more than that. So to get an idea of the answer you're going to be expecting, we know that it's going to be less than a kilogram, because if a person ate a kilogram of this toothpaste, it's going to be 2,800 milligrams that they're ingesting, which is obviously more. But our answer was 2,390 from the previous question, so we're not too far off that. So the answer that we're going to get should be less than a kilogram, but actually not that much less. So to work out the toxic mass that the person can have will just be the 2,390, which is the maximum allowed. And this toothpaste has 2,800 in a kilogram. So we're just working out the fraction of this kilogram that the person can eat and stay under the toxic limit. And that is 0.854 kilograms. So we can see that is under the 1 kilogram, but also it's not too far away. Now some students during the exam did this calculation the other way, so that's why it's always a good idea to try and have a rough estimate of the type of answer that you're going to get, because if you've done this calculation and got an answer of over a kilogram, then you know there's something wrong going on. So with a lot of these calculations, it's best just to do a quick initial estimate just to get a rough idea, and if your answer is roughly that, then you know you're on the right tracks. Question 3 is going to involve a calculation as well. We've been told we've been given some hydrated sodium carbonate, which is heated for a minute, to try and calculate how many waters there are per molecule of sodium carbonate. We've been given various values of the mass of the evaporating dish and its contents at various stages during the experiment. So the first thing we need to do is calculate how much sodium carbonate we've got. So we've got the mass of NaCO3. So what we're assuming here is the dish after heating just contains sodium carbonate and all the water is gone, and the empty dish is obviously with nothing in it, so the mass difference will just be sodium carbonate. So that's going to be 24.92 minus 24.35, which gives us 0.57 grams of sodium carbonate. So next we need to work out how much water there is. So the mass of H2O. So here, before any heating, that's got the sodium carbonate and the water, and we're going to assume after the heating all the water's gone. So the difference between these two figures is going to be the mass of the water. So that's going to be 25.47 minus 24.92, which gives us 0.55 grams of water. So now we've got the masses of each of those, we've got to work out how many molecules of each they are. So the mole of NaCO3 is going to be our mass of sodium carbonate, 0.57, divided by the molecular mass of sodium carbonate, which is 106, and that comes out to be 0.0054 moles of sodium carbonate. So if we do the same thing for water, so we know we've got 0.55 grams of water and the molecular mass of water is 18, so that gives us 0.0306 moles of water. So the next step is just finding the ratio of the number of molecules for each of those. So what we are going to do is divide by the smallest value, which in this case is 0.0054. So if we do 0.0054 divided by 0.0054, and that's going to be in ratio of the 0.0306 divided by 0.0054. So now we can work out what the exact ratio is, and that gives us a ratio of 1 to 5.68. So x in this value is going to be 5.68. So this question is saying that the correct value for x is 10. We've got to suggest a reason why the difference between the experimental value for x and the correct value. So in this case, we know that x should have been bigger, so the mass of water should have been more. So the difference between before and after evaporation, there should have been a bigger difference. And the reason that we haven't got this big difference is because we didn't evaporate all the more water. So where we assumed the difference in mass accounted for all the water that was gone, if the mass after heating still contained some water, we didn't have as big a mass difference as we thought they should be, and therefore we got a smaller value for x. So the answer for this is we didn't evaporate all the water. Okay. So part 3 says, suggest how the procedure could be improved using the same apparatus to give a more accurate value for x. Just want to point out here it says using the same apparatus. Some students in the exam actually changed the apparatus or added something else. We can't do that. We've got to use the same apparatus as was said in the question. So all we need to do this is heat it. Okay, heat it for longer. Now the best way to do this is just to keep heating it until we get a constant mass, because if the mass doesn't continue to drop after heating it, we know we must have got rid of all the water. So the suggestion would be to heat until we get a constant mass. And our justification would be to make sure all the H2O has been evaporated. So question 4 is asking us to identify some sodium compounds. Now in the question we've been told that we've been given solid samples. Now a lot of these tests involve working on solutions, so we've got to make sure that we, in the method, we're making them into solutions. And some students during the exam didn't do this, so they lost marks for it. So it says outline a logical sequence of test tube reactions that the student can carry out to identify these compounds. Include observations you'd expect to make and give the equations including state symbols for any reactions that would take place. So the three compounds that we've got are a carbonate, a fluoride and a chloride. So the first one that we could fairly easily identify is a carbonate, because if you add an acid to a carbonate, then it's going to fizz because of the release of CO2. So it says outline a logical sequence. So the first thing that we're going to do is add nitric acid. To all three. Okay. Then the next thing we're going to do is add water. So we can make them into a solution. And the third thing that we're going to do is add silver nitrate, because then silver nitrate should be able to determine which is a fluoride and which is a chloride. So the observations that we'd expect, that if it's Na2CO3, it will fizz with the acid. Okay. If it's NaCl, it will give a white precipitate with the addition of the silver nitrate. And if it's NaF, we won't get a precipitate with the addition of silver nitrate. Okay, so 3 steps, we should be able to identify them. So the equations of the reactions that we would get with those additions. So for Na2CO3 plus 2HNO3, we get 2NaNO3 plus CO2 plus H2O. So the state symbols for these, so these would be aqueous, of course CO2 would be a gas and the water would be a liquid. So for the silver nitrate reactions, we'd have N3 plus sodium chloride, and that would give us silver chloride plus NaNO3. So again, looking at the state symbols, this would be aqueous, this would be aqueous, this would be a solid because this is all precipitate, and then this would be aqueous. Then the third reaction, we'd have AgNO3 plus NaF, and that would give us NaNO3 plus GF. So again, got aqueous. Now, because this doesn't form a precipitate, it's still going to be aqueous, as is this. Okay, so we've got no precipitates there, they're all in solution. So question 5 is about equilibrium. So we've got this decomposition between sulfur trioxide and sulfur dioxide and oxygen. We've been given delta H. We can see that it's a plus value, so we know that this is going to be endothermic, okay, and that's going to be important for later in the question. The graph in figure 4 shows the concentrations of sulfur trioxide and the oxygen over a period of 6 minutes at temperature T1. So the first part of the question is state the time to the nearest minute when equilibrium is first established. So we know when equilibrium is established is because the concentration levels will level off. Okay, there'll be no apparent increase or decrease of the reactant or the product. Now some students tend to put where the concentrations equal. That's not the case. It's when the concentrations level off, so there appears to be no more reaction taking place. So in this case, that's about 3 minutes where we start to get a straight line. So the time is 3 minutes, and the explanation is the concentrations remain constant. So part 2 says sketch on the graph how the concentrations of the sulfur dioxide changes over the 6 minutes. So if we have a look at the equation again, we can see that for every molecule of sodium trioxide that is used, we get 1 molecule of sulfur dioxide. So however many of these are used up, we'll get the same number of sulfur dioxide molecules used. So in this graph we can see we started at 0.4 molar and we've ended up with 0.1 molar of sulfur trioxide. So that means there's been a decrease in 0.3 molar. So that must mean there's going to be a 0.3 molar increase in sulfur dioxide. And the reaction is going to take the same amount of time to actually reach equilibrium. So we know that it's going to be after 3 minutes, and we know it's going to be 0.3 molar. So we know we're going to get a straight line round about here. We know we're starting with 0 moles, so now it's just a case of joining them up. Okay. So the third part of the question says the temperature of the mixture was changed to T2 and the mixture was left to establish a new equilibrium. In the new equilibrium, the mixture, the concentration of sulfur trioxide was found to be 0.07. So if we remember in looking at the graph, originally it reached equilibrium and it was 0.1 molar of sodium trioxide was left, and now there's less. So what it means is the reaction is shifted to the right hand side, so there's been more product made. So if we go back to looking at the equation, because there's less of the sodium trioxide, there's going to be more product made, so the reaction is shifted in this direction. And we know that the forward reaction is an endothermic reaction, and it will shift in the endothermic reaction to try and cool down the reaction. Okay, if you remember, the changes that happen to try to combat, to try to negate the changes that we've made. So by going in the endothermic reaction direction, we're trying to cool down the reaction, which means we must have heated up the reaction from the previous temperature. So therefore, T2 must be higher. Okay, so T2, the second temperature, must be a higher temperature because the reaction to try to combat this has tried to cool it down by going in the endothermic direction. So the explanation is equilibrium has shifted to the right hand side, or the endothermic direction, to decrease the change in temperature. So question 6 is going to have us look at the change from a liquid state to a gas state. So the student has got a volatile liquid in a syringe, and they're going to inject it into a gas syringe and heat it up so the liquid is vaporized and turns into a gas. So we've been given various numbers, we've been given the mass of the syringe before and after injection, so we'll be able to find out the mass of the liquid using this. We've got the oven temperature, atmospheric pressure, and the increase in volume in the gas syringe once it turns to a vapor. Now, things to note with this is we're going to have to do some conversions. So at the moment it's in degrees C, so we're going to have to change that to Kelvin. We've also got this pressure that's at the moment in kilopascals, so we're going to have to make sure we convert that into pascals, and at the moment we've only got this in cubic centimeters, so again we're going to have to convert that into the appropriate format for the equations. So the first part of this question, it says define the term relative molecular mass. So this is just the average mass of one molecule divided by a 1/12 of the mass of one atom of C12. Now note it's asking for the molecular mass. Some students will give the definition of atomic mass, so make sure you give the correct one. So the procedure we're going to use is use the ideal gas law for this. So we know that the number of moles is PV over RT. So remember to convert the pressure to pascals and the volume, and R we've been given as 8.31, and again convert the temperature to kelvins, that's 371.1, and that comes out to be 2.81 times by 10 to the minus 3 moles. So we've been asked to work out the relative molecular mass. So we know the number of moles. So MR equals the mass of the liquid that we had divided by the number of moles. So the mass of the liquid we had was 0.21 grams, and we just did that by calculating from the mass of the syringe before and after injection. The number of moles is 2.81 times by 10 to the minus 3, and that comes out to be 74.7. Said some of the liquid injected did not evaporate because it dripped into the gas syringe outside the nozzle. Explain how this would affect the value of MR. Okay, so the best way to do this is have a look at the equations that we've used to calculate and see how that would translate to a change in our MR. So if we didn't have all the liquid going into the gas syringe, then what would happen would we wouldn't get as big a volume change. So this would be smaller than we'd expect, and that would give a smaller value for N. So if this is a smaller value than we would expect, then MR would actually be larger than it should be. So if we go down to this, how would it affect the results? So the MR would be greater than the true because we'd get a lower volume than we should, because less of the liquid has vaporized into a gas, so it will be a smaller volume. So question 7 starts off by asking us about oxidation states. So we've got the equation of chlorine and water here. It's deduce the oxidation state of the chlorine in the HClO and the oxidation state of the chlorine in HCl. So here you've got to remember under what conditions the other molecules, the other atoms will have certain charges. For example, when does oxygen have -2, when does hydrogen have +1, etc. So in this case, we know that the oxygen is going to be -2. And we know that hydrogen is going to be +1. Now, in this state, there's no overall charge. So all the charges have to balance to 0. So in this case, Cl is going to have a charge of +1 to make sure that this has no overall charge. In HCl, the hydrogen is going to be +1. So again, to make this molecule have an overall charge of 0, the chlorine is going to have a charge of -1. So the next question is asking us about the half equations, which is the movement of electrons during the reaction. Now, very few students actually got this right during the exam, so it's worth practicing your half equations. So in this case, we've got Cl2 plus 2H2O, and that takes us to 2Cl minus plus the 2 electrons. Now we could have put the protons in here as well, so it would have been 2HClO plus 2H plus in there, but you'd have got the mark just by ignoring the protons in this. So for the reduction, we've got the Cl2 plus the 2 electrons, and that gives us 2Cl minus. And again, we could have included the protons, so we'd have had a 2H plus on this side, and we'd have ended up with 2HCl, but we'd have got the mark for the equation that we've just written there. So it says give an equation for the reaction of sodium hydroxide in the manufacture of bleach. Now this equation is given in the specification, so it's just a straight recall. And any equations or definitions that are in this specification you should learn, because they're easy marks. They're going to just be a pure recall question like this. So I would go through the specification, either write out or highlight any equations or any definitions that are given in that, because only 23% of the students who sat this exam managed to recall that equation, and it's already there in the specification for you to learn. So it's just 2NaOH plus Cl2, and that goes to NaCl plus NaClO plus 2H2O. Right, so this question is going to ask us to do a calculation. So we've been given the equation. Now things to note with this, we've got a ratio of 2 iodines to every ClO minus, and we've got a sample of bleach which was found to contain the ClO minus ions at 0.0109 moles per dm to the minus 3. The potassium iodide was added to 20 cubic centimeters. Calculate the mass in milligrams of potassium iodide needed to react with all the ClO minus ions. Give your answer to the appropriate number of significant figures and give one observation during the reaction. Okay, so the first thing we need to do is, we've been given the concentration of ClO minus ions. We've got to work out how many ions are in this 20 cubic centimeters. So the number of moles in that volume is just our concentration, which is 0.0109 times by our volume, which is 0.02, remembering to convert from cubic centimeters, and that gives us an answer of 2.18 times by 10 to the minus 4 moles in that 20 cubic centimeter portion. So we're going to have to work out how many moles of potassium iodide we're going to have to add that to that. Now remember, we need to add 2 for every molecule of the ClO minus. So the number of moles of Ki is going to be the 2.18 times by 10 to the minus 4 times by 2, because that ratio, and that equals 4.36 times by 10 to the minus 4. So we've been asked to calculate the mass in milligrams. So the mass of Ki is the number of moles, which is 4.36 times by 10 to the minus 4, times by the molecular mass of Ki, and that equals 166. And so that gives us a value of 0.072376 grams. We've been asked to give the answer in milligrams, so we just need to multiply this answer by 1,000, which will give us 72.4 milligrams. So we've also been asked to give an observation during this reaction. What we'll end up with is a black solid forming. We could have also had a brown solution, we'd have got the mark for that. Some students put about fumes coming out or about a purple solution. You wouldn't have got the answer for a purple solution or talking about fumes. It had to be either a black solid or a brown solution. Okay, so we've been told now that we've got a reaction where potassium chlorate decomposes to produce potassium chloride and oxygen. We're asked to give the equation for the decomposition of potassium chlorate and use the data in table 3 to calculate the enthalpy change. So the reaction is, the equation is just going to be our starting reactant, which is KClO4. We've been told that that decomposes to potassium chloride, which is KCl, and oxygen. So the important thing here is just making sure that the equation's fully balanced. So now we've been asked to calculate the enthalpy change for this reaction. So our enthalpy change is delta H, and that is going to be the enthalpy for the KCl, which is minus 436, and we're going to take away the enthalpy of formation for the KClO4, so that is minus 434, which gives us an answer of minus 2 kilojoules per mole. Question 8 is asking us to look at some data from a mass spec to do with Br79 and Br81 ions. We've been told that the ions are accelerated to the same kinetic energy and they travel through a tube that's 0.95 meters long. The Br79 ions took 6.69 times by 10 to the minus 4 seconds. So the first thing we're asked to do is calculate the mass in kilograms of one Br79 ion. So we know that 1 mole of Br79 is 79 grams. Now that means that Avogadro's number of Br ions will have a mass of 79 grams. We want to work out the mass of one of those ions, so it will be the 79 grams divided by Avogadro's number, which is 6.022 times by 10 to the 23. Now this will give our answer in grams. We want to know the answer in kilograms, so we just further divide that by 1000, and that gives us an answer of 1.31 times by 10 to the minus 25 kilograms. The next part of the calculation has asked us to find the time taken for Br81 ions to travel through. We've been given the value of how long it takes for the Br79. What we do know is they're travelling the same distance and they have the same kinetic energy. Okay, but to work out the kinetic energy for the different ions, we need to know velocity. So the first thing we need to do is calculate the velocity that the Br79 ions had. So V79 was the distance travelled divided by time, and that is, the distance is 0.950 divided by the 6.69 times by 10 to the minus 4 seconds that we've been given. So the velocity that the Br79 ions had was 1420 meters per second. So we can now work out the kinetic energy that these ions had. So the kinetic energy for 79 was half mv squared, which equals half times by the 1.31 times by 10 to the minus 25, which we'd calculated in the previous part, times by the velocity squared, which is 1420 squared, and that gives us an answer of 1.32 times by 10 to the minus 19 joules. So now we know that the kinetic energy of 79, we know that the kinetic energy of the 81 isotope must be exactly the same. So V81 is going to be the square root of 2 times the kinetic energy divided by the mass equals, so root 1.963 times by 10 to the 6, which equals 1.40 times by 10 to the 3 meters per second. So now we know the velocity. The time taken is going to be distance over velocity, which equals the 0.950 divided by the velocity we've just calculated, which is 1.40 times by 10 to the 3, which equals 6.80 times by 10 to the minus 4 seconds. So a lot of students made this more complicated than it needed to be by putting in extra steps. So as long as you realise that they both had the same kinetic energy, so to work out the kinetic energy of the first one where you had the relevant information like the distance and the time, then you were able to basically go in the opposite direction once you had a value for kinetic energy. So 8.2, it says explain how ions are detected and the relative abundance is measured in a TOF mass spectrometer. So what happens is, as ions hit the detector, they gain an electron. So the relative abundance is proportional to the size of the current that's generated. So for the 2 marks here, we just needed to know that the ion gains an electron when it hits a detector, and that will give us 1 mark. And the relative abundance is proportional to the size of the current generated. So question 9 is looking at molecular shapes. So we're asked to draw a shape of a molecule of KrF2. It says include in your answer any lone pairs. And again, make sure you do this because quite a few students during the exam didn't do this. And name the shape produced by atoms of KrF2 molecule and suggest a bond angle. So we have KrF, and the lone pairs we've got like this. So the molecule is linear and the bond angle is 180 degrees. Now some students didn't get that it was linear, and I think they were trying to take into account of these lone pairs pushing these bonds. Now what we've got to remember, this is a 3D shape. So the structure as a whole is trigonal bipyramidal, but these electrons here are perpendicular to the 2 Fs. So imagine the Kr and the 2 Fs sticking up and down like this. Now these 3 pairs, lone pairs, are sticking out at 90 degrees to this plane. So this is where we've got the lone pairs. So we've still got this bond angle as being 180 degrees. It says there are 2 lone pairs of electrons on the oxygen atom in a molecule of oxygen difluoride. Explain how the lone pairs of electrons on the oxygen atom influence the bond angle in oxygen difluoride. So we know that lone pairs repel more than bond pairs. So if we put that for 1 mark, lone pairs repel more than bond pairs of electrons. Therefore, what's going to happen is the bond angle will be lower than we normally get in a regular tetrahedral. So therefore, the bond angle will be lower than regular tetrahedral, because they're being pushed together because of those more repelling lone pairs. So we'd expect an angle of round about somewhere between 103 and 106 degrees. So Silicon tetrafluoride is a tetrahedral molecule. Deduce the type of intermolecular forces in SiF4. Explain how this type of intermolecular force arises and why no other type of intermolecular force exists in a sample of SiF4. So the type of forces that we're going to get are van der Waals. Forces. And the way that these come about is we get an uneven distribution of electrons in one of the molecules. So this just happens spontaneously. The electrons are moving around, and at any one instant, one of the molecules will have this uneven distribution of electrons. And this induces okay, so that's an important word to have in the answer. Induces a dipole in a nearby molecule. And again, it's important to say that it induces a dipole in the molecule. So basically what's happening is if you've got an uneven distribution of electrons, then you're going to find part of the molecule has a small net overall negative charge where the electrons have accumulated. Now we know that negative charges repel, so in a neighbouring molecule, this negative area in one molecule pushes away the electrons in a nearby molecule that's near it, and therefore that part of the molecule becomes slightly positive, making another part of this nearby molecule slightly negative. Okay, so that's how you induce these dipoles where you've got an uneven distribution of charge. So it says, explain how this why no other type of intermolecular force exists in SiF4. So what we could say is because there's no hydrogens, in the molecule, then there's going to be no hydrogen bonding that takes place. Okay, so only less than 5% of students got full marks for this. Most students realised that it was van der Waals, but very few were able to describe how those forces arose or why there weren't any other forces present. If we now have a look at the multiple choice questions, so the answer to the first one is C. So here many students forget about the ionic bond that exists between the ammonium and the chloride. Question 11 is C. So here you remember that nitrogen gas is N2. So you've just got to work out what proportion of a mole you have in 6 grams. So it'd be 6 divided by 28, the molecular mass for N2. Then once you know the fraction of a mole that you have, multiply that by Avogadro's number, so you know how many molecules of N2 you have, and then multiply that by the number of protons that you have in N2, which is 14. So for number 12, the answer is D. So that's just recalling your trends from your notes. 13 is D. So here you've got to remember or realise that you've got 3 times as many F2 molecules reacting as N2. So if we have 60 cubic centimetres of fluorine, then that's going to react with a third of 60, which is just 20 cubic centimetres of nitrogen. So you're going to have 10 cubic centimetres of nitrogen left over. Now for every 1 mole of N2, you're going to have 2 moles of NF3 produced, because it's a 1/2 ratio. So if we've got 20 moles of, or 20 cubic centimetres of nitrogen gas reacting, we're going to end up with 40 cubic centimetres of NF3 produced. But don't forget we have the 10 left over from the unused N2 gas, which is going to give us our answer of 50. "14 is magnesium, which is just a recall question. 15 is B. So many students remembered that barium sulfate is used in medicine for imaging. 16 is C. So again, we've just got to remember the difference between oxidizing and reduction. 17 is B. Again, we'll have discussed this in class, and so recall question. 18 is B, which again you're going to have to recall your trends graphs. So this one is D. Now what we've got to remember is we've got 150 grams in 500 cubic centimetres. So we're going to have to remember that in 1,000 cubic centimetres there's going to be 300 grams of ammonia. So got to double this amount, and then it becomes a simple concentration calculation. But some students went wrong just by taking this value rather than the value that would be in 1,000 cubic centimetres. So the answer to this first one is A, and that's just to make sure that the solution is thoroughly mixed. So you're not taking different concentrations from different parts of the actual flask. This one is just rinsing out with water. If we used alkali or acid to rinse out the conical flask, we're going to alter the concentration of the solution. "22 is use a less concentrated alkali in the burette." This is because if it's a strong concentration, then a drop can make a very big difference. But by using a less concentrated alkali in a burette, then you can get a more accurate value when you're adding, because if you imagine a drop in a small volume is much more significant than a drop in a large volume. So this is work gloves while measuring out the acid. Hopefully that you've all carried, when you work with acids in the lab, you are wearing gloves. Another reason why you're wearing gloves. And the final question is red to orange. Now, a lot of students went straight to what colour it would be if it was a change to alkali. But don't forget, it's not going to an alkali solution first, and that's not where you're stopping the titration. You're not stopping the titration when it goes to alkali. You're stopping it when it goes to neutral, which will be an orange colour.